seen that in order to correctly express a measurement result, it is necessary to associate it with an uncertainty, usually expressed as a standard uncertainty, and that from this it should be possible, starting from the probability distribution of the values that can reasonably be attributed to the measurand, to derive the expanded uncertainty, that is an interval of values about the measured value, with a given coverage probability. We have therefore concluded that a measurement result is never expressed by a single value, but by an entire interval of values. At this point, the question arises as to how to compare two measurement results in order to determine whether they are the same or different. In other words, we compare two measurement results to decide whether they refer to the same measurand or to two different measurands. We cannot do this by comparing two numerical values because, as we have seen also experimentally when we discussed the type A evaluation method of uncertainty, it is very unlikely that we always obtain the same value from repeated measurements of the same measurand. We would end up thinking that we are always measuring different measurands. We therefore need to compare two intervals, and several scenarios are possible. The first is the one you see represented graphically here. For the two measurands x1 and x2, we have obtained the same measured value and the same expanded uncertainty. So, the measurement results are expressed by exactly the same interval. This is the only case in which we can say in a strict mathematical way that the two measurement results are equal, but it is also a case that does never occur in everyday practice. Another possible case is the one you see represented graphically here. In this case, the intervals of values that can reasonably be attributed to x1 and x2 are different and have no values in common. This means that none of the values that can be attributed to x1 can also be attributed to x2. So, the two measurement results are different and we can consider that they represent two different measurands. Let's now look at the case you see represented graphically here. In this case, neither the measured values nor the intervals built from the expanded uncertainty coincide. However, all the values that can reasonably be attributed to x2 can also be attributed to x1. Therefore, we cannot state that the two measurement results refer to two different measurements, but neither can we say that they are the same. It is therefore said that they are metrologically compatible. The case you see represented here is quite similar. Some values that can reasonably be attributed to x2 can also be attributed to x1. So once again, we must conclude that the two measurement results are compatible, as we cannot state that they refer to two different measurements. Bear in mind that this also applies in the limit case that you can see here, and that very rarely occurs in practice, where the two intervals have only one common point at their extremities. Even in this case, we cannot state that they refer to different measurands, and therefore we must conclude that they are compatible. Let us now see how to express this concept of metrological compatibility in mathematical terms. If we were dealing only with numerical values, we would say that the two values are equal when their difference is zero. Conversely, we would say that they are different when their absolute difference is greater than zero. However, we have seen that a measurement result is given by a set of values. If the two results are compatible, we expect their difference to fall within an interval about zero, the width of which is given by the expanded uncertainty of the difference. By knowing the standard uncertainties u of x1 and u of x2 associated with x1 and x2, and their covariance if the two measurements are not independent, We can find the combined standard uncertainty of their difference by applying the uncertainty propagation law, which we covered in another video. You can see the result here. By multiplying this value by an appropriate coverage factor k, we obtain the expanded uncertainty shown in this equation. We can therefore state that the two measurement results refer to two different measurements if the difference between the measured value x1 and x2 is greater than the expanded uncertainty with which it has been evaluated. Mathematically, this is expressed by the relation you see here. It follows that metrological compatibility, which occurs, as we have seen, when we have no grounds to state that two measurement results refer to two different measurements, is mathematically described by this relation, that is, when the absolute difference between the measured values x1 and x2 is lower than or equal to the expanded uncertainty with which it has been evaluated. At this point, we can fully understand the definition of metrological compatibility given by the VIM in Article 2.47. Property of a set of measurement results for a specified measure such that the absolute value of the difference of any pair of measured quantity values from two different measurement results is smaller than some chosen multiple of the standard measurement uncertainty of that difference. Usually, that certain multiple of the standard uncertainty is actually the expanded uncertainty we have considered so far. Metrological compatibility is often also expressed using the normalized error. As you can see here, it is obtained as the ratio between the absolute value of the difference between the two measured values and the expanded uncertainty with which that difference has been evaluated. It is nothing more than the ratio between the two sides of the inequality we have seen so far to mathematically express metrological compatibility. Therefore, two measurement results are compatible if the normalized error is lower than or at most equal to 1, whereas they are not compatible if the normalized error is greater than 1. In the case where the two results are uncorrelated and therefore the covariance is 0, the denominator becomes the square root of the quadratic sum of the two expanded uncertainties assigned to x1 and x2, as you can see here. To summarize, we have seen how to compare two measurement results to determine whether they refer to the same measurement or to different measurements. We have seen that it is not possible to obtain a correct result by considering only the measured values. The measurement uncertainty must be also taken into account. We have therefore discussed the concept of metrological compatibility. This is an important concept in metrology and in many of its applications, including legal ones, because it prevents us from considering two measurement results as different simply because the measured values differ when in reality they do not. Many disputes, including legal ones, could be avoided with a metrologically sound comparison of measurement results.